In this video, we're going to talk about how to report statistical results. So you've already chosen an appropriate statistical test and ran your model, but how do you report the output? First, what should you report? You will want to report both the statistical results as well as a narrative conclusion that goes along with the statistical results. The specific statistics that you report will differ a little bit from test to test, but in general, you'll want to include the test statistic and any corresponding degrees of freedom. This is the T statistic or the F statistic, for example. You'll want to report the p-value that corresponds to the test statistic. You will also want to report measures of effect size and a confidence interval around that effect size. Finally, in addition to these statistics, we also want at least a brief narrative conclusion telling readers what these statistics mean in the context of our specific research question. On a note about decimal places, we typically report statistics to 2 decimal places. Sometimes you'll see 3 decimal places, particularly for p-values or very small statistics that are only meaningful at that 3rd decimal place. Sometimes you'll get very small p-values. When your p-value is less than 0.001, you'll simply report p is less than 0.001. Now I want to talk about how to interpret p-values. This is often one of the most confusing parts of interpreting statistical results, and it's where a lot of people go wrong and misinterpret their statistical results. If your p is less than the alpha level that you set, for example 0.05, this means that your result is statistically significant. In this case, you can say, we found support for our research hypothesis. You can also say results were consistent with the research hypothesis, or that the result was statistically significant. This is all common language that you can use to describe a result when a p-value is less than the alpha level that you set. In contrast, we want to avoid saying things like, our research hypothesis was correct. This is because we need to account for the possibility that we made a type 1 error, or a false positive. That is, it's possible that we found a statistically significant result in our sample, but our hypothesis may still not be true in the population. Similarly, we never want to say that we found proof. The reason for this is we rarely, if ever, prove something in science or research. Instead, we accumulate evidence in support of or not consistent with a given hypothesis. Over time, with consistent results, we may become more confident in a finding, but we still don't want to say that we've proven something beyond any doubt. We also don't want to say that the null was incorrect. Again, we need to account for the possibility that we've made a type 1 error or a false positive. Finally, we never want to say anything about the probability that the null or alternative hypothesis were true or not true. In null significance hypothesis testing, the p-value tells us about the probability of the data if we assume the null hypothesis is true. It doesn't tell us the opposite. That is, it doesn't tell us about the probability of a hypothesis given the data. This is a little bit counterintuitive. Oftentimes what we want to know is how likely is it that our hypothesis is correct. But this isn't what the p-value tells us, and it's important not to make this important mistake. If our p-value is greater than our alpha level, this means that our result was not statistically significant. In this case, we might say, we did not find support for our research hypothesis, results were not consistent with our research hypothesis, or the result was statistically non-significant. All of these are appropriate ways to describe a statistical result when the p-value is larger than our alpha level. But just like with significant results, there are ways that we want to be careful not to describe non-significant results. For example, we don't want to say that our research hypothesis was incorrect. We need to account for the possibility of a type 2 error, or a false negative. That is, an effect might not have been statistically significant in our sample, but the hypothesis could still be true in the population. We also never want to say that we found support for the null hypothesis. We either reject or fail to reject the null hypothesis, but we don't find support for it using this type of null significance hypothesis testing framework. We also don't want to say anything about the probability that the null or alternative hypothesis is true or not true. Just like I described on the previous slide, the p-value tells us the probability of the data given a hypothesis. It doesn't tell us the probability of the hypothesis given the data. And finally, we never want to say anything about the results being almost statistically significant. In some fields, it's common to report marginal significance or trending effects. In that case, you want to pay attention to the norms of the field and perhaps do some reading on both sides of that debate. But regardless, we want to stay away from language such as almost or nearing significance. Moving on from p-values, I want to talk a little bit about reporting and interpreting effect sizes. Effect sizes and confidence intervals around those effect sizes can provide important additional information beyond just whether a result is significant or not. This is important because we could have a statistically significant effect that's really tiny if we have a large enough sample. In that case, the result might be statistically significant, but not necessarily practically meaningful. On the flip side, we could have a statistically non-significant but large effect due to a really small sample size. There are various guidelines available for interpreting effect sizes as small, medium, or large. For example, Cohen's guidelines, or an updated guidelines by Funder and Ozer in 2019 from a psychology perspective. You can use any of these guidelines, but be sure to cite your source so that people know what guidelines you're using. Finally, I want to talk a little bit about using causal language when reporting statistical results. If your predictor variable is manipulated, like in an experiment, it's okay to use causal language. We can say that X caused Y, the predictor caused the outcome, X influenced Y, or language like that. But if our predictor variable is not manipulated, if it's measured or observed, like in a correlational study, we can't use causal language. Instead, we might use language like X was associated with Y, X was related to Y, X was correlated with Y. Finally, there's a special case where, in a longitudinal design, if X precedes Y, we can also say X predicted Y. But we still want to be careful not to use causal language such as X caused or influenced Y. Let's look at an example. Consistent with our hypothesis, the intervention significantly improved performance. I'm then reporting the t-value, which is the test statistic, with the degrees of freedom in parentheses. I'm reporting the p-value, and because it's smaller than 0.001, I'm just writing p is less than 0.001. And then in addition to information about statistical significance, I report that the effect was large. I cite my source because there are different guidelines out there for what's considered a small, medium, and large effect. I report the effect size, which in this case is Cohen's d, and a 95% confidence interval around that effect size. In this case, I am using causal language by saying that the intervention improved performance rather than that it was simply related to performance, because this is describing an experiment. However, if I was describing a correlational study, for example, the relationship between age and performance, I would instead want to say that age was significantly associated with performance. You'll notice that this example includes both statistics as well as a brief narrative summary that links these statistics to our research question. And causal language is okay in this case, but only because I used an experimental design.